Okay, so moving onward. The next one we want to take a look at is, let me get that put together. So we did that one and that one. All right, the next one we're going to take a look at is a three-part one. It is one very similar to what we did in class. I'm going to move a little bit more quickly on this one. We have an inclined plane with no friction that they identify, which is at 36 degrees, like so. We have a block, 4.47 kilograms, and it is set on the frictionless ramp and let go from rest. It is marked that it is some distance up the ramp. For me, it's 3.3 meters. Okay. First thing that they asked is find the acceleration of the block. Now, we did this in class, and if you check your notes, there is a general solution that we can go through and we can actually check for. I'm going to refrain from doing that because I've warned you before that general solutions are not necessarily the way that we want to go about this. It does not show an understanding of the problem or the physics involved. It simply shows the ability to plug numbers in like a good little monkey. So what we're going to focus on instead is how to solve this properly and demonstrate that you know how to apply the physics. I'll remind you that on the exam, I could very well ask this question, except include friction, for example, as we did a lab that includes that. All right, so they want us to go through and find the acceleration of the block. Well, to find an acceleration, as we've seen, we either need to use kinematic equations, which I will save you some time. We do not know enough information, despite the fact that we now have a length. Or we need to look at the forces acting on the object. Now, take a look at your class notes because I brought up that this is one of the few times in which we do not want to use our regular coordinate system that looks like this. Instead, what I advised you to do is to try and put all of your acceleration in one direction. Well, since it's going to accelerate down the hill like this, I'm going to make plus x down and to the left. I'm going to make positive y up and to the left. Now, this will be slightly different from what you saw in your notes because I think the last time I drew this, it was down and to the right. Doesn't actually make much of a difference. All right. Now, the upside of this is it puts all of our acceleration in one direction, which is actually the best way to minimize the work that you have to do on any problem like this. So, we're going to go forward based on this. I need to draw a free body diagram, and my free body diagram is going to look like this. I have a normal force that sticks up off of the plane. Remember, if this is my plane, then the normal force is so called because it comes off at 90 degrees. Remember, in math, normal means 90 degrees. It's another word for perpendicular. We've got gravity. Gravity goes straight down, like so. And as a result, because of our new coordinate system, where this way is positive x and this way is positive y, we now end up with the following. Components to our force of gravity. We went over how to determine this in class, 36 degrees. Whatever the incline is, the angle of the incline will actually be here. It's the angle between your force of gravity and your new y component. And we talked a bit about that in class. You can imagine that we took the regular coordinate system and we twisted it by 36 degrees. So we'll end up with this being 36 degrees. All right. Now, just like we've done in class, we can apply Newton's second law, which would be great. I would draw out the sum of forces in the y, but we know that there's nothing really interesting happening in the y direction because the block is not sinking into the ramp or jumping up off of it. We chose this coordinate system, so all the interesting stuff is happening in the x. So sum of forces in the x direction equals positive fgx. It is positive because fgx is pointed down the ramp, which is the way that I set up my positive x direction. And that's the only force in the x, so that'll be equal to my mass times my acceleration in the x. Well, we're going to need to find the force of gravity in the x, so let's see. We've been given the mass of the object, but it turns out that that's actually extra. You don't need it. We can find our force of gravity, which is going to be equal to mg, which for our numbers was 4.47 kilograms times 9.81 meters per second squared. I think in this one, let me double check, it says that the acceleration, I apologize, I do this a lot. It says that the acceleration due to gravity is 9.8 meters per second squared. So we'll use the one that the problem gives us just to be safe. Okay, so force of gravity, let's solve for this guy. 4.47 times 9.8, not my regular 9.81. We find that the force of gravity is 43.81 newtons. It's actually 806. All right, so here's our force of gravity. This is not the entire force that's pulling it down, or I should say, this is actually greater than the entire force that's pulling it down the ramp. Because this is the full value right here. This is the 43.8 that we just found. Part of it is in the y and part of it is in the x. We want to find what's in the x. So this is my angle, 36 degrees. Here's where that vector stuff comes back in. Remember, there's 90 degrees between my x and y directions. So there's my right triangle. And we end up with the following. Sine, SOHCAHTOA, so sine of 36 degrees equals my opposite, FGX, over my hypotenuse, FG. I can multiply both sides by FG. And we just found FG. We found that it was 43.8 newtons times sine 36 degrees equals FGX. FGX equals, so sine 36 times 43.8. We end up with about 25.7 newtons. All right, 25.7. That's actually FGX here. So I'm going to have, let me write this back out. This is from my sum of forces in the x direction. FGX equals my mass times my acceleration in the x. 25.7 newtons equals my mass, 4.47 kilograms, times my acceleration in the x. My acceleration in the x, dividing both sides by 4.47, should come up to about, to three significant figures, I get 5.76 meters per second squared. Let's double check. Let's see. 5.76 meters per second squared is the answer that they have listed. The final thing that I will bring up is this. We talked about this in class, that we have a general solution when you're dealing with no friction on an inclined plane, that you would find that the acceleration is equal to g sine theta. Check your notes on that. But we would end up with 9.8 meters per second squared times sine of, in this case, 36 degrees. Sine 36 times 9.8 gives, oops, sine 36 times 9.8, 5.76 meters per second squared. You may use this general solution to double check your answer, but if I were to ask you this question on the exam and you have only this written down, then you would have the correct answer, which is usually only worth about 2 points out of 25. You will do very badly. I'm not looking for you to be able to plug numbers into an equation. I can teach a computer to do that. I'm looking at your ability to be able to apply Newton's laws of motion to make predictions about how things will move. All right, so that's part one. On the upside, that's actually pretty much the toughest part, at least from what I saw. Next thing is, what is the block's speed when starting from rest? It has when it travels 3.3 meters along the incline, which takes us back to this picture. Starting from rest, our initial velocity is 0. Our displacement is going to be 3.3 meters in the positive x direction with my new coordinate system. Again, this is where that coordinate system is paying off. 3.3 meters. V final equals That's actually what we're looking for. They're asking how fast it's going. V initial in the x is 0 meters per second. It starts from rest. And we have just found that the acceleration in the x was 5.76. 5.76 meters per second squared. We do not know the time, nor do we care about the time, which means, here's where you need to go looking for your kinematic equations. But the kinematic equation without time is v final squared equals v initial squared plus 2a delta x. This is the next question, so I start plugging these things in. V final squared equals 0 meters per second, 1 to t squared, plus 2 times 5.76 meters per second squared times positive 3.3 meters. That guy has a whole lot of zeros, so 3.3 times 5.76, helps if I put this into my calculator properly, times 2, I end up with the following. V final squared equals 38.02 meters squared per second squared. But I want the final velocity, so I need to take the square root. V final equals 6.17 meters per second. Let's double check the answer that they have for us. 6.17 meters per second is the correct answer. All right, so now we've got that. Final question is, what is the magnitude of the perpendicular force that the block exerts on the surface of the plane? First off, this was the second question in that series. Now they're asking us kind of a weird question. They're asking us the perpendicular force that the block exerts on the surface of the plane at a distance of 3.3 meters down the incline. The way they may have it drawn, it's not at the bottom of the incline. It's basically in the same type of situation we have here. You could redraw your free body diagram, but we've already got one. As it goes down the hill, it still has the same forces. It's still at the same angle. We're still on the surface of the Earth. And as I mentioned before, the perpendicular force, well, they're talking about the normal force here. Now, that doesn't mean that all perpendicular forces are normal forces, but it's the one that's in question. In fact, they're asking you about the force that the block exerts on the ramp. So they're asking how hard the block pushes down on the ramp. Well, as we've talked about a bit before, that's a Newton's third law pair with this guy, which is how hard the ramp is pushing up on the block. So in this case, what they're actually asking us for is the normal force on the block, because it's a Newton's third law pair with the normal force of the block pushing down on the ramp. Okay, well, let's check. We did not actually solve for that yet because I told you that we were ignoring the y direction, but this still fully applies, so let's take a look. We've got the following. Sum of forces in the y equals my normal force minus the force of gravity in the y, our new y direction. And that's going to be equal to my mass times my acceleration in the y. We know the acceleration in the y is 0 because that's how we set up our coordinate system. We didn't have the block jumping up off the ramp nor sinking down into it, so we get the following. My normal force will actually be equal and opposite to the force of gravity in the y, not because of Newton's third law, because of Newton's second law. The Newton's third law is how we're going to take the normal force of the ramp holding up the block and find out what the normal force is of the block pushing down on the ramp. That is a Newton's third law pair. For this, we need one more thing. We know that cosine of 36 degrees equals my y component divided by my total force of gravity. How do I know that? Once again, free body diagram. The adjacent side in this triangle to 36 degrees is my y component. I'm using a bit of trigonometry. The adjacent side would get me cosine, and so we end up with the following. Multiply both sides by the force of gravity, and I get the force of gravity in the y equals, what did we have, 43.8, that's my total force of gravity, times cosine 36. We end up with the following. If I've done this correctly, 35.4 newtons. And we end up with 35.4 newtons. There's our answer. As I mentioned before, depending on what you're asked, sometimes solving the forces in another direction, it may not give you an answer that you're looking for immediately, but there are a lot of times that we follow up with other questions, so it's not like it's wasted time, and it's certainly not wasted practice. All right.